right, so let's begin. Today we talk about, it's a scary title, probability mass functions. It's almost like we're in a math class. Our math class is statistics. We use math as a tool. But it is kind of a scary title if you're not used to this. That's fine. We'll get through it. This is kind of the second half of the hypothesis testing. So hypothesis testing, the one we did on Tuesday, is kind of like it completes the pair. Okay? So today we're going to talk about probability mass functions. Okay. So you can plot the probability of any value for a variable. It's just what I'm saying is you can make graphs. The probability of all possible events equals 1. So what I'm saying is you're going to plot the probability of the score of the various possible scores for a variable. Well, let's think of a variable like flipping a coin. Zeros and ones, heads and tails. So if you have zeros and ones, you're counting the number of heads. Do it like that. What's the probability of a head? It's 0.05, or 0.5, I'm sorry. What's the probability of the tail? It's 0.5, isn't it? Right? 50-50 chance. Don't give me crap about it. Well, maybe it's more weighted on one side. Or what if it lands on its edge? Shut up. Just don't do that, please. It's a theoretical coin, okay? It's a theoretical, completely fair coin. By the way, the bias in a coin, it's a real thing. You actually could measure it. You can measure it. I've read papers like this. This is somebody who's like, I need a publication. Let's flip the coin a bunch. That stuff actually is real, but it's so small it doesn't matter. So we can still use 50-50. So the probability of a head is 0.5. The probability of a tail is 1. Because there's only two possible events, they each have a 0.5 probability, add up to 1. Think of a sporting event. Let's go with the hockey game because I like hockey. Montreal's playing Detroit tonight. I don't know who's going to win. I know who I hope will win, but that doesn't matter. But one team will win and one team will lose. Right? There's no in-betweens. There's no ties. There's no ties in hockey. There used to be ties in hockey. I don't know why there aren't ties. Ties are fine. But anyway, that's it's a philosophical thing about sports. So with the probability, I don't know the probability of Montreal winning, and I don't know the probability of Detroit winning. That's not something I can calculate. But I know the probability of either Montreal or Detroit winning is 1. It can't be that nobody wins unless they cancel the game. Nobody's canceling any hockey games. It takes a lot to cancel a hockey game. Entire cities burning down like Los Angeles. They're like, okay, we'll take a day. Professional sports is big business, right? So the probability of Montreal or Detroit winning is 1. Because that's the two possible outcomes. You could get a 0, a half, a 1, a half, 2. There's 20 possible marks you can get on one of my quizzes. 21, because there's 0, and then all the way up to 10, and there's halfway increments. If I add all those together, I get 1. The probability of them. I don't know what the probability is. I could go calculate it. But the probability is 1. You add them all together. So the probability of all possible events is 1. Does that make sense to everybody? I see a lot of nods. It's nice to see. So that means if we plotted this as a graph, so we're plotting it, we're making a graph. The area under the curve equals 1. Okay? So if we actually calculated that area, it equals 1. Let's give you a very quick example here. A dice, a single die. There are 6 possible outcomes, 1 to 6. The probability of each is 1 over 6. The height of each of those bars is 1 over 6. 1 over 6 times 6 is, look, it's 1 again. It's always 1. The total of all possible events is 1. If we added all these up, it's 1. The area under the curve is 1. Now, I know, actually, these are discrete events. Okay, for all you really mathematically inclined people, don't worry about that. I'm doing this as a, I don't know, for illustrative purposes. You can see that, right? 1, 6 times 6 is 1. It's 1. The area under the curve is 1. Oh, I just took a shift. Right, shifted into second gear. The normal distribution is here. Everybody's favorite distribution. We all, of course, have a favorite distribution. I'm partial to the Poisson distribution. Some of these are just for me. Pretty much all of them. There are very few statistics. Jokes. Yeah, that's a normal distribution. You know the normal distribution. Let's put it over there. Make it a little smaller. The most common, or at least the most useful one to us, and it's just a probability distribution. Okay, they're just probabilities on the x-axis and scores on the probabilities on the y-axis and scores on the x-axis. So instead of just points for 1 to 6 die rolls, because again, those are discrete events. Here, this is a continuous variable. That means all these values are possible. So I've been using human height quite a bit as an example. Let's stick with that. So heights can take a wide range of possibilities. In fact, we could almost say they're continuous, right? Between 0 and, I don't know, tallest person ever, 8'11". I don't know what that is in centimeters. Because we weren't using metric when you gotta understand again, I was an odd kid. Tried to memorize the Guinness Book of Records. I was a very strange little boy. When it's harder for you to do other things other kids do because you can't see that well, you know what you do? You do weird things like, I think I'll try to just memorize the Guinness Book of Records. My brain is full of useless shit. It's unreal. Anyway, and as my brother often says, we haven't really discounted the possibility that everything he says is complete and utter bullshit, have we? He says this whenever I say things like, the world's tallest man was 8 foot 11.1 inches tall. Born in England, he had glasses. I remember that. I remember a picture of him. I can't remember his name. Anyway, it's way over here, and then there's way over here. Because there's a lot of real small people. They're called children. Right? By the way, on average, the average person has more than one skeleton in them. Because some people are pregnant. Dude! The average human has more than one skeleton inside them. Isn't that weird? Because some women have 2 skeletons inside them. Some have even more. That's a fun one. You can win. That's a good bar bet. Because you just have, what's the average number of skeletons inside somebody? Everybody's 1. Nope. All right. So you can see then that instead of just points, now we got a whole thing. The whole area under this whole curve is 1. If you take a look at a Z table in any textbook, in your textbook, and anywhere else, you'll see that the numbers, if you add all those probabilities up, add up to 1. They add up to 1. So the characteristics of the normal distribution, as we've been talking about already, of course, it's unimodal, and it's symmetrical. We can talk about its shape, and it's bell-shaped. And for most of our purposes in this course, that's all we need to know. That's close enough for rock and roll for most things we do. It's going to be fun. But if we want to look at the sort of background of why this is useful to us, if we want to look at why this is useful, well, why is normal distribution useful? It's because many variables in the natural world actually are distributed. Their probabilities are normal distribution. Human height's a great example. We probably, if we took kids out of the equation, so we probably just have adult humans, people over 18, we get a nice normal curve for height, and for weight, and for IQ. IQ's actually built that way. The cool thing is that a lot of variables are like this, are normal. Or they're just assumed to be normal. Which isn't always the best idea, but it's a pretty good approximation. There's a lot of things that aren't normal that we assume are normal in introductory statistics textbooks. So you may have seen, I don't know if Dwayne does homework assignments in 2126, but you'll see questions in the book that'll say things like, assume the distribution of the life of a light bulb is normally distributed. There's no damned way it's normally distributed. Because a company that made light bulbs that failed as often as they worked forever would go out of business. It's just not going to happen. So it's going to be skewed to the left, right? Fine. But we assume things are normal because it's a pretty good approximation of a lot of stuff. And then if we have a standard distribution, hell, it's called, when we do a couple things to it, a standard normal distribution, we can use techniques that are going to be the same every time we do something statistically. That's why this is super useful to us, right? And the other thing is sampling distributions by the central limit theorem, which we'll go over when we talk about t-tests on Tuesday. But you will, I hope you remember the central limit theorem, because the central limit theorem says that x bar, the sampling distribution of x bar, all the possible values an average can take, is normally distributed with a mean of mu sub x, and a variance, or that's the standard deviation, I'm sorry, of sigma divided by the square root of n. This is just notation, so that means normally distributed, mean of x, standard deviation of sigma divided by root n. The thing is, this is the distribution of the mean, the sampling distribution of the mean. So it's kind of weird because the distribution we're talking about here is if we did the experiment a lot, an infinite number of times, which is a lot, and we then calculated the mean and plotted what mean we got. So let's use human height again, and we'll use all the Algoma University students. So at least here, it's hard enough doing that. We're not going to factor Brampton in right now, okay? So it's all of us up here. We're going to be sampling 10 of you. And getting your heights, writing it down, getting the average. And then we'll do it again, and we'll do it again. And we'll do it an infinite number of times, because apparently we have a very big grant and a lot of free time. So we do this, and we actually get a distribution of the average of the averages. And you might think, but you can't do that. And what do I keep saying? Numbers don't know where they come from. You can do anything you want to them. You torture them enough, they'll tell you anything. It sounded like I was endorsing torture, and I don't. It's a controversial take. I think torture's bad. The way the world works now, that might be. Anyway, there's a lot of math that I'm not going to go into because I can't remember most of it that says this is true. We would expect if we were taking averages of 10 people and then plotting it, average 10 people plotted. This part's easy. If the average height of Algoma University students is 175 centimeters, which is the number that we've established that I made up the other day, and if we took the average, we still would get, we would expect 170, what did I say, 175, 175. We would expect that. That just makes intuitive sense, doesn't it? Does it or does it? If it doesn't, I can show you some very complicated math, but if I was taking samples of 10 people, sometimes I'm going to get the whole men's basketball team. It's going to happen. Maybe too tall. Sometimes I'm going to get the whole, I don't know, where are short people? I can't start them. Sometimes I'm only going to get women who are in first year, so they're younger and shorter. There you go. That'll work. Women are not as tall as men. Younger people are a little bit shorter than older people. So if we get a whole bunch of 18-year-old women, and that's going to happen too. So sampling, they're going to be a little shorter. They're not going to be as much of an outlier as the whole men's basketball team. But I'm trying to think of something on the other direction. But normally we would expect something around 175 for an average, and that's, so I hope that's, so it'd be, have the same mean as the population mean. So the mean of the means has the same value as the population mean. The harder one, intuitively, is this, the variance of the standard deviation. I hope you can see. It's hard to believe you could hear. My voice went up so high there. It's like higher than the garage doors are closing and opening. Even dogs can hear my voice. Oh, you can see here that what would happen if we had, what if we sampled 10 people, and we're talking about, we get a number. If we plotted that up, we get a number, we calculate a standard deviation. We can do that. What if instead instead of sampling 10 people, we sample 20 people? Well, we'd still get the same mean from the sampling distribution. But what would happen to our standard deviation? Well, and don't worry about any formulas right now. Let's just think about this. If I keep sampling, and I get, so I get a bunch of 10s, then a bunch of 20s, then maybe I'll do a bunch of times 30, what's going to keep happening is my estimate gets better and better, isn't it? Because if I sample everyone, my estimate's perfect. That's no longer an estimate. So if I sampled 10 people, it's pretty variable. If I sampled all the people, it doesn't vary at all. It doesn't vary at all, can it? Because if I take an average of, I don't know, how many students are there here? I don't know, let's say 4,000. I'm making up a number. I have no idea. No one shares anything with me. And that's the way I like it, by the way. I don't want to know anything about how the university works. I just want to do my job. I don't care about anything else. Anyway, I like you guys. You guys are fine. You're good. Not fine. Fine's a C. You're at least a B. You're good. Other people, like Keo, this is all, I hope you know it's all over. Anyway, what am I going to do here? I don't know. Get everybody, if I do that all the time, it's going to be 0. If that n, when that n thing gets bigger, okay, I don't have that written there, good. I didn't write this because I thought it might frighten you, but I'm not going to write it. Does anybody remember taking the limits of functions in high school math? Did they teach you limits in high school?
I think they did, but I don't remember.
Okay, so at least they tried to teach you. And the rest of you just weren't paying attention in math? Okay, good. It's okay. It's a really easy thing to follow. It really is. We've got a quantity sigma over the square root of n. Okay? What happens as this gets really big? What happens as n gets really big? It must get really small. It gets smaller and smaller. What happens if n... What happens if n approaches infinity? What happens to that quantity if n becomes infinite?
The answer is infinitely small.
It gets smaller and smaller, but how small does it eventually get?
Like almost close to 0.
In fact, as it approaches infinity, it approaches 0. So in fact, this mathematical expression is the limit as n approaches infinity of sigma over square root of n is 0. Okay? Because a fraction works like that. The big number on the bottom, the thing gets smaller. And I hope you can see as again, if we sampled everyone all the time, the variance would get be 0. We'd keep getting the same number, 175, 175, 175. Let's see, if you calculate 175 minus 175, that's 0, and we do that a whole bunch of times, it's 0 divided by the number of, it's 0. So as n increases, the standard deviation of the sampling distribution of the mean approaches 0. In other words, it stops being a sample, it starts becoming a population, because we've calculated everything. So that's why, for example, the more subjects you get in a study, the more accurate your estimate is. Now, you all knew that. You could probably intuitively know that the more subjects you have, the better, because you're getting closer to the population. Mathematically, that's why. It's because of the central limit theorem, but because we use that in statistics. Questions on this? Okay, good. I probably didn't think I was going to spend 15 minutes talking about that expression. I don't know what I thought I was going to. Okay, properties of this distribution. I just made a distribution up. I've never seen a triangular distribution. I don't think it's even a thing. So, if we were looking for the probability of getting a value of somewhere between 3 and 7, we could just do the area of this, I don't know, house-shaped object inside. And if we did that, actually that'd be easy. This is a weird case where this would actually be easy. How do you do the area of a rectangle? Length times width. Some of you were going, don't ask me. Here's a better one. How do you do the area of a triangle? Remember that one? Half base times height? Yeah. Should have paid attention more in school. Stay in school, guys. You're in school, obviously. Just should have gone. If you go back in time, pay a little more attention in about grade 8 math, and you feel probably a lot more confident right now. But I think y'all get this, right? So if I was saying that these are the two probabilities, I can just get the area under that curve. I could get that rectangle, that triangle, add them up, and I got my answer. I suppose I could do that. I hope you realize that's not how we do this, but we're going to do something similar, actually. We are going to calculate the area. We just aren't going to do it by using half base times height and length times width. Because typically, I've never seen a distribution like that. They don't look like that. They don't look like that, do they? It's too bad, because that'd be easy. That would be easy again, simple geometry. But if it's not a common shape, like a square and a rectangle, or a rectangle and a triangle, or I don't know, a rhombus, trapezoid. What do we do then? Then you have to know calculus. You don't have to know calculus, don't get frightened. I just saw a look on somebody's face, I could have sworn you looked very frightened there. Like that. You don't have to know calculus, it's okay. But this is all based on calculus, and calculus is super cool, and you should probably know some calculus because it's cool, but you probably have other things to do, right? So no time to just learn calculus for fun? Okay. It actually is kind of fun. It's creepy how cool it is. This is just notation, by the way. And it just says taking the integral of the variable, of the function f of x, between 3 and 7. All this says is take the area under the curve between 3 and 7 of the function f of x. That our function, I don't know what the function is, I'd have to, yeah, it's actually 2. Yeah, whatever. So this is just a mathematical expression of finding the area under the curve between 3 and 7. Okay. And this thing does look like an S. It's supposed to look like an S, but it's an integral sign. Okay, so that's actually how you would do it. You would then take that integral, and you might be looking at that going, but I don't know what those squiggles mean. And that's fine. Someone else did, and they figured it out for you. So it's too bad that you didn't take any calculus in school, but somebody did the calculus for you. Okay, and you really, it's just even the basics of calculus you need. Like, you know, the thing, this was figured out, how to do an area under a curve, and I'm not going to have how it's done, but this was figured out by some guy, what's his name, Isaac Newton, and yeah, just some nobody named Isaac Newton. He just sort of discovered calculus. Oh, and the guy named Leibniz in Germany also did. They were at the same time. And what he did is he said, okay, if we had a curve like this, and if we just approximated the area under the curve like, I don't know, we could do a couple of rectangles and get those areas. We go, yeah, but that's not good enough. Let's make more. Like that, like that, that. You make the rectangles smaller and smaller and smaller and smaller and smaller and smaller. And if they get small enough, there's no error anymore. So when you get an infinite number of rectangles, you get the area under the curve. And you sum, that's why it's an S, you sum all those areas together. It's like, how do you sum an infinite number of techniques? That's half a calculus. The other half a calculus? There's I'm just trying to show you how cool calculus is. I mean, this is, you don't have to know any of this stuff. This is just neat. So if we have some curve, I'd like to know the slope of that curve right there. How do I do that, right? Because the slope of a curve is easy, rise over run, but not with something that isn't straight. So how do you do that? I'm going to tell you that let's pretend that this is y equal and this isn't. Let's say that's y equals 4x squared. It's not. Let's pretend. You take the 2, you multiply it times the 4, 8x. That's the acceleration. That's the slope of that curve. Isn't that wild? Like you multiply the exponent times the coefficient. Like the basics of calculus are that's trivially easy to understand. And the fact that our universe works like that is kind of weird, and I always kind of look at that and go, that's weird. There's some weird stuff. So that's why I say it sucks that you don't know calculus, because it's just neat to realize that the universe works like that. It's wild. So if you can learn some basic calculus just for fun, seriously, like just watch a couple videos, it's really cool stuff. But, so okay, I know you don't know calculus, but I'm going to show you something. That's the function for the normal distribution. So f of x, or y, equals 1 over sigma times 2 pi, square root of 2 pi, times e to the negative x minus mu divided by 2 times the variance. What's e? Okay. Do you know what e is? You know what calculus is, you know what e is. E is the base of the natural logarithm. It's about 2.71828. It's like pi, it's just it's a natural, it's a constant. It's just something in the universe about how the universe works. It's the base of the natural logarithm. Right, so if you took a logarithm of, like, remember, base 10 of 10 is 1. The log, base 10 of 100 is 2. So that it's basically what a log is, a logarithm is, it's the exponent that you would multiply the base by. The exponent that you would do to the base. So look, 10 to the 1 is 10. 10 squared is 100. 10 cubed is 1,000. Why am I telling you that? Because there's another kind of logarithm called natural logarithm, or it's either called ln, or you might see log to the base e. So the base isn't 10 anymore, it's 2.718281828. You go, what? It's a lot of weird things in nature have that constant. Okay? Including the function of the normal distribution. And look, pi's there too. Pi, again, it's just, you know about pi because you would have ran into that in school, right? Pi r squared and all that. And you go, well, why is that? Well, it just is. It's just a constant. So e is just another mathematical constant, just like pi. I can tell you that integral, use a technical mathematical term, is a real bitch to solve. That's hard. In fact, I don't know that you can do that one easily. I mean, I know I couldn't. Yeah, so you just take the integral of that function. Go ahead, have fun. That's really hard. I don't even know that you can do the integral of that. But if you could, you then put 95 and 100, let's say you want to find the probability of having the IQ between 95 and 107. Those weird stats questions that we give you in second year stats classes. So we give you one of those and you say, you don't do it by looking things up in a Z table, you do it by doing a couple of integrals and then plugging these values in. Okay, fine, you can do it that way. I had a friend in grad school used to do stuff like that. She didn't have a psych degree, but she was doing a psych PhD. She had 2 degrees in math. But she also was interested in animal behavior, and she took some courses, worked in a lab, but she could just do math like that. Like her statistics, in her statistics tests in grad school, she would just, well, from first principles, you don't really have to figure it all out on your own. But she could, because she had a math degree. For the rest of us, I suppose we could do it that way, but we don't happen. I'm never going to ask you this, by the way. I don't know it offhand either. So don't get too worried. So we can make it a little bit easier. What if we made the mean 0 and the variance 1 a standard normal distribution? That's actually a lot easier. That's an integral, I think, that's a lot easier to take, that integral. when you calculate it, it's called taking an integral. So if I was taking an integral of this side here, that's way easier. Because I put zeros in for mu and ones in for variance. Standard deviation. Oh, is that why the Z distribution is used so much? Because the math's easy. It's because the math's easy. This was done, the reason we have standard distributions and the standard normal Z distribution is because it makes the math easier. Okay. In fact, it turns it into really a mechanical arithmetic problem and not a math problem. So we can make it a little easier by doing this, by turning it into a standard normal distribution. Okay. So questions still at this point? You okay? Again, this is just getting you the background, okay? I'm not going to ask you. I can't teach calculus. I can't. I don't remember enough of it. Like, I remember the basics, but you get past the basics, and I'm like, oh, yeah, okay. Oh, the product rule. I can't remember it. There's all kinds of rules about doing calculus, and I can't remember anything. So don't worry. But I know theoretically it's calculus behind it. Whoops. I was disconnected, maybe? Or is my pointer? Yeah, my pointer's in the wrong place. Okay, so still this isn't easy, but it's not horrible. So that's a Z distribution. So this is why we take things that are in a normal distribution and turn them into Z scores. When we say turn them into Z scores, well, we look them up in a Z table. We do that because somebody did the calculus for you with a mean of 0 and a variance of 1. Some poor graduate student back in the, actually that probably wasn't a graduate student here, it was probably Gauss, but whoever did this, I can't really remember who did it. It's got to be Gauss, right? Yeah, probably. Anyway, Gauss and some of his students probably calculated this stuff for you. So all those percentage points of the Z distribution, somebody did a bunch of calculus and went, okay, if the mean is 0 and the variance is 1, what's the probability of getting a value of 1.6? This, and they write it down, put that in the table. Okay, 1.7, do the next one. They write it down. Somebody did that for you. Every time you look something up in a statistical table, I want you to just think to yourself, thank you, unnamed graduate student from 100 years ago. It's very kind of you to have done this for me. Or maybe even longer, maybe 150, 200 years ago. And they did it by hand. And they didn't have phones, much less smartphones. They didn't even have phones. So what we do in this case is we look up 95, we find out the probability of that is negative 0.32. I'm not going to show you how to do that, you know how to do that. Right, so you look it up in a Z table. Same thing here, 0.466. I'll show you in a second. There's actually an even easier way than looking it up in a table. There's a website you can use that works really well. Or, I mean, I did this with my calculator, because my calculator is a statistical calculator. So it has the normal distribution in it and the t distribution, so I can do t-tests and normal distribution percentage points using my calculator. The calculator I bought on my first day of grad school that had money lent to me by a guy who later had to quit his job as a professor due to sexual harassment. But that's an entirely different story. I thought he was a good guy. Turns out, not a good guy. But he lent me $20 to buy a calculator in 1988, which he got back, and he also helped me move once. Also, he's horrible. Anyway, so my calculator can do that. Yours might. Doesn't matter. It does or not. The important point is that we can look these things up. We can look it up, and I'll show you a web tool in a second that works really well. And it works really well. But you don't have to do that. You can also just, I'm sure you learned how to look things up in a Z table. And there's, of course, a Z table in the back of our book. So some poor bastard did the calculus for you, like I said. You look at we just look these things up in a table, or there's a handy dandy web tool right there. So if you use that tool, and I'll show you what the output looks like in a sec. This guy's got a ton of great statistical stuff on his website. Like, it's great. You put the values in, it gives you percentages. I encourage you to go play with that when you get a chance. It's really not hard to play with. It looks like that. So what did I do here? I went to the normal distribution part of that link, and I think that link leads directly there. And I said, let's see, the mean of 0 is standard deviation of 1. And I want to find out what it is between negative 0.32, because I calculated that at the z, and positive 0.466, and it tells me. That's pretty quick. You can do that with a z table, of course, right? You could have looked up what this one was and what this one was, and then done some arithmetic. This is done for you as well. So I have no problem. Use this. I mean, it's great. I use it all the time. I use it all the time. So the reason we changed from a variance, oh, this was IQs, right? So we had a mean of 100, variance of 225, standard deviation 15. We had that, and we converted it into zeros and ones. I can tell you, by the way, if you go on here and you take this and you turn this into a mean of 100, a standard deviation of 15, and whatever, what were our two numbers? Was it 95 and 107, is that right? And if you put 95 and 107 here, you get the same answer. Because all doing that to a normal distribution, like turning into a distribution of 0 and 1, all that's doing, it's just transformations. We talked about transformations earlier. See, there's a reason I do things in a certain order. I actually thought this, I'm hard to believe it may seem. So the reason we go zeros and ones is because we have tables, and it made the calculus easier. But actually today, we don't really necessarily need tables if we have this. You're not always going to have that, though. But you will always be able to look something up in a z table. So I don't know last year when you took 2126 if Dwayne showed you this website. If you did, great. If you didn't, it's fine too. Learning how to do this with a table is a pretty important skill. Okay, questions. I know this stuff is a little bit different than what you normally get in classes that start with PSYC. Okay, remember though, these lectures are designed to not be very long, so we have time to talk and answer questions and sort of tutorial the hell out of this thing, so we can. Don't be afraid to ask anything. Well, some things, I mean, you know, some things you shouldn't ask me, like, I don't know, aliens. I don't know what I'm doing. You know, the bus wasn't coming. Anyway. It screws you up completely, right? Because you get up in the morning, you're like, I know what I'm doing, I have a plan. And on Thursdays and Tuesdays, I can get up at like 7:30 and I can ride 10 kilometers on my bike trainer. And then I can do everything, and then the bus doesn't come and everything falls apart. Well, okay, I gotta ride more for my life. So it's really not that big a deal. Remember, some poor bastard did your calculus, so you don't have to. I think back to these people doing this 150 years ago, not even having adding machines, doing everything with pencil and paper. So you and I can go, oh, okay. It's pretty cool. And just honor those people, because nobody remembers who they are. We all remember who, Gossett and Fisher. Fisher was a racist, and Tukey. And these guys are great statisticians. But we never remember their graduate students who probably did all the calculations for them. So we just look it up on a table or use the handy-dandy web tool, and you're in business. It's really not horribly difficult. Now, how often do you ever get asked a question, or you ask the research question, how many people have an IQ between 95 and 107? Well, clearly never. This is done for teaching. The Z test that you've been taught, and then you look, geez. I used the Z test once my whole career, and it was in my PhD dissertation. Like, that's how long ago it was, and it's like one extra analysis I did in one experiment. And I still keep looking at it going, it's a Z test? How is that possible? Right, it does happen, but it's not something we use that much. But it's the basis for everything else. Everything else. Like, a chi-squared distribution is a z distribution squared, for example. So chi-squared with 3 degrees of freedom is z squared plus z squared plus z squared. an F distribution is a chi-squared divided by its degrees of freedom divided by a chi-squared divided by its degrees of freedom. They all are related. It's all the same stuff. Deep down, the math is all the same. It's the kind of thing I sometimes wonder, if we just required you to take, like, I don't know, 3 semesters of calculus, then we wouldn't have a program. But the 3 people I taught stats to would really know it. Our program would die. You must take a whole great deal of math as well. I don't think people go, yeah, that sounds fun. But part of me kind of wishes we did. I really wish actually you had to take some math, like 3 credits of math. I think it's valuable. In a lot of places, you do have to take a first-year math class to take stats. All right, this isn't scary. It could have been scary. Some of this stuff, if you haven't seen this kind of notation, is really scary looking, isn't it? This makes me look like I'm a professor. Take a picture of this. I feel very professorly. That feels very professorly, and I'm going to send that to my mom, to our family group chat, and say, look, I'm a professor. That just looks mathy and professory, doesn't it? So that's kind of scary, but just looking stuff up on a table isn't that bad. And the important thing, and this is lost, I think, a lot of people, again, the reason when you're doing problems like this that we have in 2126, not in a course like this, is we say, do this, then this, then this, then this. You must write out this and this and this, then draw a picture, and then write a decision rule. Like, we do that for a reason. It's so you think about these things. And drawing the picture is one of the biggest things you can do. Because when you do that, you can say, okay, I need between here and here. It's really an important thing to do. All right, questions on this stuff? We'll stop recording in a second. We can do some general questions if you want. We got time left. I can show you a couple other things as well. Okay. That.